does it mean for us as building information modeling experts to provide all the IT infrastructure that our team need to support the exchange of information they have? As I said, we will be starting from the very basic, from the ground of information technology today. In general, when we talk about information system, we are referring to the combination of all of these. The technical infrastructure that you need, the data that you have, the process and the procedures that you put in place on top of this, and of course, last but not least, the people who collect and need this data. So we are today focusing on the very ground levels. Data and infrastructure. In terms of data, we start from the very basic principles. We started looking at binary codes. We started looking at the hardware level of information technology. We try and understand what it means to, what a file format is. How can we extract information from it? So in that sense, what are databases that we can mine and leverage for our processes? And we'll be looking at a bit of infrastructure in terms of hardware, just to recognize that there is a need for computing power, nothing more than that, and networking. That's probably more interesting. Networking is very rapidly becoming much more relevant every year because it allows us, given the threshold that it has surpassed in the past few years, networking is now the one way that we have to communicate between all the stakeholders. So, just because you have a piece of wire connecting to a computer doesn't mean that you have the suitable network for your needs. So we'll try and look at what are the requirements for our networking as well. Please interrupt me anytime. So today is a very informal session, very slow-paced, but dense in terms of content. So whenever you are, whenever you think you're missing something, if you have a doubt, raise your hand, ask me a question, no doubt at all. It's we try to make it very informal. So if you look at literature, computing is terribly simple. Computing is just like that. You have some sort of input, you have some sort of processes, you do your math, you do your calcs, you run an algorithm on your data, and then this produces an output. Super simple. Things get much more complicated very fast if you start looking at who are the people that use these things. And you start saying, well, there is no input if there is no user. There needs to be some level of user requiring the execution of some processes. But processes and users are far from each other from a computational standpoint. They need an intermediate layer of hardware to execute the transaction of the input. Very frequently they need to rely on some operating system to support an application that considers that there is an input. And the same happens on the way back. Whenever you have produced some level of output, that output is still in the domain of your application, whatever your application is, and it needs to be migrated down to the users through the features that an operating system provides and through any level of hardware that is available and to the user. How many of you are familiar with the difference between all these layers? What is an application, what is an operating system, hardware, and well, users are easy. It's us. If I ask you to describe what an operating system is, would you know that?
Like Windows and Mac OS?
Yes. That's all two examples. Yes?
I was going to say, for instance, like Windows 8, is it like the interface that you see that you can interact with?
Yes, that's what we perceive. So operating systems for us, at the very early approximation, are the user interface that we have to rely on, right? To deal with. So if you are running on your telephone, you have an operating system. You have a software that controls the general behavior of your hardware. Okay? On top of that, you can install any number of other applications. So you have your apps for your phone, and the same you can do for a personal computer or a Macintosh or any other hardware. But that's not how things necessarily are, and it's certainly not how things used to be. Operating systems are a fairly recent invention. In the past, hardware were custom defined and customly designed to run a specific application. There was no intermediate level of operating system. One hardware was born to run a simple application. So there was no disconnect there. The operating systems are born with the need to have standard hardware, like any of these computers in front of you, that can run any number of arbitrary applications that you can buy separately. Okay? So to make this thing easier, you devise the idea of an operating system as a software that allows you, or better, allows the software developers to rely on an abstraction layer for the hardware. They don't need to know if you have a large monitor or a small monitor, or 2 printers or 3 printers or a plotter or anything like that. All of that complexity is dealt with by the operating system. The application, my software that I'm developing, only needs to deal with the business logic of my needs and an abstraction layer. I know that there are some functions that I can rely on to actually print, to actually show something on the screen, to actually receive text from the user. I don't have to go and code the behavior of the A key on my keyboard. That's something that the operating system does once and for all the applications, right? So that's something that is evolved in time as we have progressively matured the level of maturity of the computing industry. Another view of this process can be quite different and goes like that. Humans are not in the picture anymore. We still have computing science, computer sciences and information science, when input, output and storage are disconnected from humans. These can be things that happen autonomously from our needs. Now, of course, in the end, some of this storage will be exploited and used by some user at some point. But I just want to make it clear that there are currently in the industry a lot of processes that are kick-started automatically by timing processes or by events that are measured by machines in complete autonomous behaviors. Okay? So now we have a nice abstraction of what computing is. A black box says we do something with our data and we transform some output out from the input. This is important to know because this allows us to say, well, we have to be very careful then of what the input is and the output is, because only on specifically crafted inputs and outputs then such processes and loops can be built. The format of this data is important. Another important thing that I kind of introduced before is that there is always, with computing, a physical layer. So we will quickly deal with that at the beginning of this module and then forget about that for a long time. But there is always a physical layer. Computing means hardware. If there is no hardware, there is no computing. You can use it in as many ways as you want. Maybe you can hire it, maybe you can purchase computing power, but at some point down the supply chain somebody will have spent money to build a physical machine that does something. In the past, computer hardware was at times something like that. How many of you have seen that first image there? No?
No?
Seen it, but never explained what it was or anything.
You don't know what it is?
Binary stuff, is it?
It is binary stuff, yes. It's a piece of cardboard, right? It's a piece of paperboard with holes. That is because we go back to this idea of storage and we say, well, okay, storage is our data stored somewhere for us to be able to read again. And in the past, the easiest way that they found to start writing information down in a way that was easy to read by a computer was punching holes on a piece of card. Okay? So, you have a big standardized piece of paper of a size that is agreed, right? And you can easily put this onto a reader. And it's easy to create a machine that puts a pin through a particular position, right? Actually, this machine will have an array of pins, right? They will be always there, and the card will move along this. And whenever the pin goes through the paper, that means that there is a hole. If there is no hole, then the pin does not go through. When the pin goes through, it touches something else, and current flows. Yeah? So you have a way to tell a machine whether some information is true or false, 0 or 1, cold or hot, whatever. Whatever it is that you need to store, you now have found a way to encode that on a physical layer. Never forget, there is always a physical layer. Oh, this is very eloquently put here. Convention. If there is a hole, then something is true. If there is no hole, something else is true. Can you see how this could work? Do you all? It's easy, right? There's no complicated stuff. Is that the only way to do computing? Clearly not, but is that the best way to store information? It was for some time, but it's not the unique way. We have decided by convention that we have two states of all these little rectangles of paper. We either punch a hole into them or not. The density of information depends on how good our hardware is at discerning two holes from each other, right? You could think of a situation where so if I go back to this idea of my standardized piece of paper, I could say, well, I punch 4 big holes, or 6, let's say, right? My reader will have 2 pins, and as the car moves along this, it can discern whether this is been punched or not, or this has been punched or not, okay? Information density is now an easy concept for you. You know that on the same piece of paper, you could define a different standard where you have, I don't know, 10, 15 or 18 different possible locations where we agree that can be a hole or not, okay? So we now have defined a standard that we must agree on, so that if I need to pass information to you, I know how to punch holes in such piece of paper. I need to know how big this is, because there's not a human that looks at it and says, well, there is a big hole. There is a machine that has a pin, so we have to agree where the pin is, up here, or down there, or in the middle, right? There is no scope for negotiation, intelligent negotiation of these things. The machine just has to work. So we have to have clearly very defined standard that says well, the minimum gap between these holes must be this big, otherwise my machine will confuse one hole with the next and the information will be lost. All right? In the history of computing, all sorts of physical tricks have been used to implement ways of storing data. An interesting one was this one here. This is a Mercury memory module, 1951, quite old. One of the problems computing has is that, well, they need information and they need to keep it updated, right? If you look back to this process here, you do some thinking, you read something, you do some thinking, and then maybe you have to do some further thinking about that. Your process is not completed. You have several intermediate steps before you come to some sort of useful conclusion of your work. Long computation and things like that. So you need a way to have a place where you store information temporarily, but reliably, and then overwrite it again and again, right? Currently we have disks that do that, right? Our hard drives or our computers do that. In the past we didn't have that technology, so this is what was used instead. It was a memory model that was based on a physical process of mercury. If you have a pipe of mercury, and then you have a sort of a little hammer, you hit one end of the pipe, and a wave of mercury will progressively move along the pipe until it reaches the end of the pipe. Okay? At the far end, you can have a reader that says, okay, there is a wave of pressure, therefore somebody has hammered the pipe on the 1 minute ago. Because it's easy to know how long it's taking to the mercury wave to propagate along, right? So if you want to save something, some information in your memory, you can say, well, I can hit the pipe or not, and if I hit the pipe, my wave will propagate. Once it reaches the end there, I will read it and copy it back in, and if I find that there was a wave, I hit the thing automatically again. So I'm kind of keeping this idea of a wave that moves along and then is reconstructed in time and kept alive until some other command comes to the system and tells it that number that used to be whatever it was, a 1 or a 0, I can read it, but I can also change it. I can write over that. I can transform that wave into a non-wave, because now I don't hit the hammer. I can write over that number, which is better than the card here, because once I have punched the hole, I cannot undo that punch and fix that and transform that 1 into a 0 or vice versa. You see? We now have one concept of storing information and one concept of storing information that we can overwrite. Okay?
But that mercury memory thing, how does that, like, is each one of those lines the same as a line on that card, and it gives a different value? Or
So, for each of the, similarly to the information density on this card, you know that you can put a fixed amount of waves in that line of mercury that you can discern, you can tell apart. Okay? So you probably have a given timing. You know that it takes, let's say, 1 minute for the wave to propagate across there, and that you can tell a wave from another every second. So you can, your sensor here is capable of distinguishing 2 waves if they are 1 second apart. That means that you can have up to 60 seconds, up to 60 waves, therefore, that are currently running or not running on that thing. And that's the information density of that.
so you're measuring the waves? 'Cause I thought it was just measuring the length of time. So it's
No, that's a constant, the physical constant of mercury. Waves in mercury propagate at a given speed,
yeah.
as they do in air, or you know. But, so basically you know that at any point you're reading whether there is a 1, a 0, a 0, a 1, a 0, a 1, a 0, or anything like that. Are you following still? Kind of, but you understand that there is a way to leave a physical trace of an idea. Okay? We have an idea of a 1 or a 0, and we are finding any physical way to keep track of that memory. Without memory, we don't have data. Without data, we don't have processes. We need that.
So that's the purpose of all this then?
The purpose of all of that is to store ideas that we can deal with. And people in time have come up with all the, something like this. This is an A4 paper, right? This is a huge machine that had, I'm not sure how many, I think 16 lines of mercury, right? And each of them stored 120 bits. That's the next step we're going to learn. What's a bit?
1,000 bytes.
No, this is odd, because we are in the third millennium, right? We are in the information age. Everybody says we live in the information age. And then if you ask people what's a bit, they would say, well, and it's perfectly normal for people to live their lives just flopping around with iPads and stuff without having the first clue of what information sciences is about. So a bit. No, my point is, don't be ashamed if you don't know these things. Just try and express your ideas. I'm used to that. It's normal. People don't know. That's why we have this session today, to give you at least a chance to ask questions that you have, and to come back to these ideas later on when you're thinking, this IT guy told me that that is impossible. Is that real or not? Because that's the market you're going to face. People in the business don't have a clue as well. So you have to have some level of understanding to say, no, I'm sure that's possible. Maybe you cannot do that, but then it must be possible. So you have to procure that function through other ways. But anyway, what is a bit? Well, a bit is the unit of measure of information. A bit is anything that can take two states, 1 or 0, true or false, hot or cold, doesn't matter. These are three things that I can store in a bit. I can discriminate, I can tell apart whether something means 0 or 1. If I have something that only takes two possible states, I can store it in a bit. So, there is a wave, I assume that means true. There is no wave, I assume that means false. There is a wave, I assume that that means hot. No wave, cold. I have an idea, and I find a way to store it. Whole, person was present. Not whole, person was absent. Whatever it is. Anything that can assume only two possible states. Right? That's a bit. So, 120 bits is nothing. Your phone has megabytes, probably gigabytes, I don't know. Right? Oh, let's go back to that idea then. Mega, giga, kappa, you know that, right? So that the scale of units, yes, that's something that we need to know. So a bit is just one bit. A byte,
1,000 bits.
or any other random number that you've heard in the past. Say again? 8, yes. One byte is traditionally, one byte equals 8 bits. So, a string of 8 bits, traditionally, is what we call a byte. Why do we need a byte? Because a bit, you cannot retake it, you need a byte at least. a bit is too small to be a useful unit of measure. You cannot really feel it, right? It's hot or cold, yeah, well, it's not, it's mild. Mild doesn't fit in a bit. It's either hot or cold, not rich enough to be a useful unit of measure. So the byte is used instead. Interesting. We have 8 bits. And then we have a kilobyte. And that's easy, because K means 1,000. So 1,000 bytes. Now, it's not that easy because very frequently you'll find that a kilobyte is 1,024 bytes. That's because of a binary convention. We'll see later, but it's about, you know, close to 1,000 bytes. And the next one up the line is megabyte, yes? And then it's gigabyte and terabyte and so on. Yeah? So, one of your MP3s is what? 3 megabytes? 4 megabytes? If you want. So we're talking about 3 million bytes. So 24 million bits. Okay? In 1951. So whenever people tell you, oh, or if you think, oh, we have seen what information sciences can do for us, it's telephones. No, you are wrong. In 1951, storing 120 bits costed a machine that was probably large as that set of tables and was probably a couple of $1 million, right? Today your telephone stores in a single MP3 file thousands of millions of times more than that. You think we've seen the impact of that? No, we haven't. We're going to see that in the next 20 years when we are all losing our jobs to computers. But we'll come to that later during the year. So, my point is, we now have an idea of ways to store information, simple information, a bit, something or something else. And now it's up to us to decide what that means. If the 0 or a 1 or the whole or whatever it is or the wave means something or something else. Then we can group this information to store more of that. We'll see how shortly. But we need a physical layer for that. This is as true today as it was in 1976 when the Apple I was born. And it was sold in a kit like that. You didn't even get the case. Right? You had to be such a type of hacker that built the case for your machine. And I'm old, but I'm 1971, so this is something I can relate to. Okay? And you should, because this is changing the life around you. That physical layer that we're talking about has been going on punch cards for ages, from 40 years. They went on trying to say, can I squeeze more holes in that piece of paper? Oh yes, you can. We can make the holes smaller, and we can make the pins that measure whether there is a hole or not closer, and so we get more data. Much more bits, much more data. Beautiful. But still, they're slow, because the card needs to go in, the pins need to go out, the current needs to flow, and slow. Can we think of something else? Yes. Other devices, electromechanical devices that will store that information in more reliable and more and faster memories, relays. And then at some point these became being mechanical, as in forces moving physical elements around, so switches, to being just electronic, as in, is there flow of current or not? So tubes and transistors produced that change, and we are talking about the 60s. Transistors. At the beginning of the 70s, transistors were integrated into chips. You all know about chips. You were born, that chips were already with us. But you are that age. You are the age of chips, right? You should be aware that you were born with them, and they are still growing. The chips we have today are much, much faster of the chips we had in 1970s, right? So people are arguing that this curve that depicts or presents the ability of computers to perform calculations per second given a fixed amount of money of £1,000. No? If you had £1,000 in 1910, you could buy a computer that would deliver this amount of computations per second, calculations per second. This is plotted traditionally for over 100 years and demonstrates some level of growth on an exponential chart. This is an exponential chart. You all know how to read this, I suppose, yes? So for each, this increase from here to there is by no way similar to the increase from here to there, because every one of these means a tenfold increase. So increasing from here to here means an increase of 1, an increase from here to here means an increase of a million, right? So it's increasing exponentially faster. Moore's law, that you're probably familiar with, have you heard of Moore's law? So Moore was one of the first AD of Intel, and he said, we are observing that the cost of producing chips that calculate doubles every given amount of time, about a year. So every year you double the power of your computer. So people have actually observed that on the long run that has been more than true. It's been more than doubled. It's actually increasing the speed of increase, in a sense. Many people argue that we have now kind of reached the limit of the current microcomputer ability to keep up with this speed increase. But there are a number of other technologies on the pipeline that are being tried right now to see whether we can find another physical substrate to continue providing that exponential growth. All right?
The DNA chips.
Say again?
The DNA chips.
They're talking about DNA chips, quantum chips. They're talking about multi-layer chips, and all of these chips are only single layer. So there is one flat net of transistors that talk to each other. Now they're thinking, okay, it's difficult to do more than that because we have reached the size. It's like similar to what we can say about the cards. It's impossible to make the holes in the card closer without confusing one with the next. We now reach that atomic level that it's impossible to make transistors smaller with them still working at a reasonable, reliable pace. So they're thinking, okay, but we can have multiple straits of this. We can have multiple chips that talk to each other. There are all sorts of ways to technologically continue to improve the speed of computing power. But I'm just, trying to point out that this is increasing exponentially. So for every year, you do all the progress that happened in the past 70 years again. Yeah? Makes sense? Every year, you gain the same gain that you gained for all the time since. What? That's what it is. We don't notice because you go out and Windows 8 is bloated. He does all sorts of things that are not needed just because he has the power to. The chips are getting so fast that software developers are lazy. They start putting all sorts of complications in the operating system and things are getting slow. Indeed, if you keep your old computer and you update the operating system, it becomes slower. Now, a computer, of course, it's still the same speed, but we're asking it to do much more every year because we are putting in much more complicated software on it. Computers intrinsically don't get old, they go on at the same speed. They just look slower because they're doing much more than they used to if you update the software. Now, we have looked at this idea of well, we'll get back to this idea of increasing in speed in the next few lectures, but for the time being we know there is a physical layer. That's what I wanted to convey. There is a physical layer. This mandates the use of Boolean or binary logic. So there is a hole, we say something, there is no hole, we say something different. That is only because it's, if you read there, currently, technically simpler to discriminate between something that has two states, yes or no, than something that has 3 or 4 states, yes, no, maybe. It's more complicated to make a machine that discerns or discriminates between a punch card that has no hole or a small hole or a larger hole. It's potentially feasible to think of a way to store this information having 2 types of holes or 3, right? A square hole versus a round hole. Yes, I can tell the difference. So I can store on that space, I can store 3 types of information, right? But it's more complicated to achieve such a machine, so people have always worked with binary states. So binary is not a godsend, it's just a technical way of solving a problem of storing information. Okay? How many of you can get that joke?
One and O being yes and no instead of 10.
Okay, that you can read this 10 and or you can read that 2, because that is the binary notation for the number 2. So the joke goes, there are only 2 types of people in the world, those who understand binary and those who don't. And if you understand binary, you get the joke. Why does this express the idea of 2?
It's 2 digits, and it's not 1.
Well, yes. No. But I love the effort. Okay, let's try and learn how we know how to count again. It's amazing the things that you don't know, guys. Not because of you, that nobody knows. That we don't know we know. Like, I think Rumsfeld said something about that, and I think Robert always played with that idea. That did it give you the
Yeah.
thing we know? No. That's his favorite. Okay, so if I have nothing, I write 0. That's easy, right? If I have one more, I write 1. That's easy, right? And if I write, I go down, I say, okay, how many things I can do before I don't have any more room to storing different information. Right, 2, 3, 4, 5, 6, 7, 8, 9. I now run into a problem. I only have 10 symbols, 0 to 9. So if you only give me one space where to write something, one box to fill in my form, right? I can only write a number there, and I have 10 possible values, 10 possible symbols. I am limited to having 10 options, 10 values, 0 to 9. Once I have exhausted all the symbols that you gave me, I need to find a trick to express larger numbers. That's the trick. And the trick is, I want more space. I need to have multiple slots where I write this information. So, in our decimal system, once we have exhausted all the 10 symbols available for one slot, we move to 2 slots. The same we do with binary. We start with a 0, we grow to 1. We have already exhausted all the possible opportunities. There is no number 2, binary, true, false, wave, not large wave, small wave. That's not an option. So the next thing I can do is use another wave, use another hole in the punch card, use another space in my form. So I say, well, 0, 1, 10. Because even here, after I did all the list, 0 to 9, I start again with 0, right? And I say, the one next it is valid for all the possible combinations I have in the first slot. So, 0, 1, 10. What's the next one? Nope. What's the next one here?
11.
11. So what I do is I start the sequence again on the least valuable item, right? So I go 1. Make sense? No. You see what? It's the same thing that you're doing for the decimal system. You try, if I only gave you numbers 0 and 1, that's because there is either a hole or no hole. You cannot have a circular hole to discriminate. You have to make do with what you have. You have only 2 options, 2 symbols. So you cannot write 12. There is no 2. There is not an option. So the next thing is to use one more space again and say 100. What's the next one?
101.
101.
And then?
110. And 101.
And then?
1000.
We got it.
Can't you go 011?
Say again, sorry?
You can't go 011.
011.
That's
We have 011, it's here, right?
11.
Oh, right.
But you write it as 11, wouldn't write it as... Or would you?
These are all zeros. All the spaces that are hidden, if you think of a decimal number, there is no doubt for you that, you know, this number here, 321, actually means no thousands, no tens of thousands, right?
Yeah.
This means 3 of the type 100, 2 of the type decades, and 1 unit. Yeah? So you add these times 10 times 100 plus these times 10 plus these times 1.
But surely in a line of binary code, if you put 3 zeros, that's 3 of each individual value for 0.
So if you're storing a number, you have a finite amount of space, and the convention is that the rightmost number is the one that is valid less. So this is valid 1, as in decimal, right? The next one is valid how much? 2 in decimal, right? The next one is valid is worth, let's go here. Let's always work by similarity, right? In decimal, this is valid 1, correct? The next one is valid worth, it's worth what?
10,
This is worth 10. The next one is worth what?
100.
100. So it's not linear, the increase, right? The increase is much bigger as we move to the left, because we are growing exponentially. So we are actually growing with the power of a number. In this case, it's 10 to the power of 0, 10 to the power of 1, and 10 to the power of 2. Right? Kind of? I don't want you to lose sleep about this. But it's important to understand that a single binary digit, a bit, single binary digit, it's a bit, that's easy for everybody, can only discriminate from two alternative states that are arbitrary. It's just one way for me to save a bit of information. Okay? But it's very poor. I cannot discriminate for complex ideas in a single bit. I need more space. So I need groups of bits. We already know that we use bytes, yeah, that are groups of 8 bits. So my next question will be, how many different ideas, is it noisy? Guys, can I ask you to, can I remind you please to be silent? It's complicated. In a byte, we can store more alternative ideas than we can store in a single bit. How many is the next logical question. And through understanding binary codes, you know the answer. And the answer is similarly to what we learned from decimal numbers, right? If I tell you how many possible alternative ideas can I store in a single digit of a decimal system. So if I have a space where I can write 0, 1, 2, 3, 4, 9, how many different alternatives idea can I store? That's 10, right? Because I have 10 possible alternative combinations. If I have 2 such spaces in decimal, how many different alternative ideas can I store? And that's 100. Because you can store 0 up to 99, right? That's very natural. It comes natural because we are familiar with that decimal format. In binary, that growth does not follow a sequence of 10. 10 to the power of 0 is 1, right? 10 to the power of 1 is 10. 10 to the power of 2 is 100. So actually, basically, just telling people, I have 2 digits available, you know that you can store 100. If you have 1 digit available, you can store 10. If you have 0 digit available, you can store none. You have no space where to store anything, right? So, in binary, that grows with the power of 2 instead. If I only have 1 bit, I can store 2 alternative combinations. And the value of that cell is 1. The value of the next one is 2. The value of the next one is 4. The value of the next one is 8. It grows, doubling every time. I can actually write this to 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. Okay? So, if I have a number like that, 1, 0, 0, 0, 1, 0, how much is it worth? it's 32, right? Because there is a 1 here. It means that I have one of those things worth 32. Plus 2 equals 34. That's very simple. So you can now store a number greater than 0 or 1 by using combinations of bits, right? And if you have 8 spaces, you have 2 to the power of 8 possible combinations. And everybody knows that that is ever seen that number before? 256? Yeah, have you ever seen those numbers before? 16, 32, 64, yeah. Because everything being stored in binary spaces, in binary cells, grows with that kind of sequence. Very naturally. So, if we it's somehow important to know that there is the need to convert our ideas into numbers, okay? For computers to be able to work. And that's how it's done for pure numbers, integer positive numbers. How do I store the fact that one number is negative? There is no sign minus, right? We don't have that thing. There is no such thing as a different symbol. We only have zeros and 1. Because it's more difficult to store, to make a hardware that discriminates, tells apart in a physical space a value that is more complicated than that. If I punch a hole in a piece of cardboard to store something, it's more complicated to create a machine that says, well, that kind of hole looks like a minus.
Could you not have something that's different shape? So where the
Yes,
hole is.
but it's more complicated. You see, it's technically more difficult to make a machine that discriminates the shape of the hole. And it's very simple to say, well, I'll make a convention. I'll just consider that if I have a number that I'm storing somewhere, I have this space, and I put a number here, and it goes 1, 0, 1, whatever it is, and I say, you know, the first space here, it's either going to be a 0 or a 1, correct? And if this is a 0, it means the number is negative. And if it is a 1, it means that it's positive. Yes? But it's easy. It's very simple to do from an information science standpoint, just to assign a conventional value to those bits. Because we're never really only dealing with 1, 2, 3, 4, and 68. We're actually dealing with complex concepts. So, as they are, computers are useless. Operating systems transform this massive amount of ones and zeros and flows of them into things that make sense to us, right? But it's important to know that when you're dealing with file formats, and that's why I'm doing all of that, because you will be dealing with DWGs, Revit files, ArchiCAD files, and everything like that, they will be ways to convert whatever idea is that you need to store into a sequence of ones and zeros. Okay? Today we'll try and look into that to really understand the difference between a drawing in AutoCAD and a drawing in Revit. And I need to tackle these to really make you understand the profound difference of the two systems. Okay? You need to understand that everything becomes ones and zeros. And it becomes ones and zeros through conventions. That first bit means positive or negative. We must agree on that. If we don't agree on that, it's just a stream of numbers. Doesn't matter how good a hacker you are. Because it's 1,000 millions of them. Try and make sense. They look like random numbers. You have to know where something starts. You have to know where something ends. What to make about all of that. Because we now have really a deep understanding of the fact that we can only store ones and zeros. Are you okay with that? Don't we use letters as well generally? You're familiar with computers. They have a keyboard. They have letters. This thing here is what we already said. I just forgot to move on with the slide, but it's telling you that the position in a number by convention makes a difference in terms of value. The same number, 1, is worth more or less depending whether it's to the right or to the left. Just as the same number, 9, is worth more whether it's in the millions or in the tens of millions or whatever, in the position of your check. You get a lot of money. Okay? So, if we know that computers, yes?
So, I'm sure you understand this. So, say for instance, from what we see on our screen, say if we just keyed in the number 2, that number 2 in binary code would just depend on, it depends on where the 0 and 1, how they're spaced out or positioned
Yes.
in relation to each other to produce what I see.
Yes.
Is that what you said?
Yes. So, somewhere in this box, there is a very precise idea of all the spaces that it has allowed, that it can write to, right? And every one of them can be associated with a meaningful interpretation, right? So, I know that in that box I put a number. I must know what type of number that is. I must know what type of convention I used to write it down. Otherwise, there is no possible way for me to read it back. Yes? So if I have the idea of a negative number, when I'm going to write it down in that space, I start with a 0. If it's a positive number, I start with a 1. I'm writing it. I mean, it's not the number is there on its own, right? At some point, some part of my computer is going to go and write it down there, right? Following that convention. Therefore, I can then read it back with the same conventional behavior. Okay? So, position matters. Every little box where you can write your numbers, you need to decide how to read it back to be able to deal with binary. Yes?
So who decided the convention, or how does the convention keep up with the infinite possibilities?
The conventions evolve for that reason. Conventions are not static. They evolve for that reason. They evolve to allow you to store progressively richer data sets. Okay? So it's not a new versions of your operating system will be developed that can do more than previous versions. Now we've had the migration from 32-bit computers to 64-bit computers. Have you heard of that? You know that when you're buying Windows now, they give you have to tell during the installation, this is a 32-bit computer or a 64-bit computer. Do you know that? Did you on the specifications of computer?
Well, I've heard,
Yeah, I've seen it sometimes, when you go to my computer and there's in the C drive section, there's the programs, files sometimes say like 64.
Exactly, yes.
80,
86, yeah.
86, it says x86 or
Yeah.
64.
And if you install the wrong software, well, it tells you that it won't install a certain software.
Exactly,
So-
yes.
So
Some
here-
software
Well,
are...
here we've got the Internet Explorer 64-bit or just Internet Explorer.
Yes. We'll come to that in a bit, but for the time being I'm just saying these conventions on how we use those boxes change all the time. And most of them are transparent to you because it's a matter of the people that are actually writing the code to do all of that. You're never going to actually decide on a specific convention. What I really want is for you to know that whatever you're doing is stored like that. And that has a deep meaning that we're going to look at in a few moments, right? So, I want you now to crack this problem for me. We know current computers deal with binary numbers only. How do you work with letters and symbols?
In binary or how we use them?
Well, how we use them, we know. We have a keyboard, there is an A on top of that, we press, we see an A blinking. Beautiful. That's what we know, right?
Yeah.
The next problem is, yeah, but how can that be? Because there is no way to go there and chisel an A on one of those bits, right? So the computer must use some sort of trick to store that A in a number and then read it back from that number, correct? Yes.
Isn't that what always so for? Just like the series and doing zeros and ones of position to determine.
Absolutely, yes. But the series is not enough on its own. We know, I mean, the position is important. So I know that whatever you are pressing on the keyboard gets transferred to me, and I will go and write it down in this space, right? From here on. 1, 2, 3, 4, 5, 6, 7, 8. Nice. For convenience, you know what? I'll store it in a byte. 8 bits. How many, so how can I store it? How can I distinguish an A from a B? Because you want to know whether you press an A or a B, right?
Positive value A, negative value every other symbol?
Possibly. Complicated though.
Yeah.
What's an easier way?
26 alternative.
Beautiful. I would say that A is 32 and B is 33. C is,
4.
and Z is whatever it is. Does it fit in a byte?
I said 26.
So, how big is a byte? That's a good question. How many different possible combinations can we write with 8 bits?
You'd need 4 of them really for A, wouldn't you?
8 times 9 times to the power of each box.
Exactly, it's a to the power of each kind of problem. And it's what to the power of what?
To the, well, I don't know.
I'll give you a hint. That should be actually your solution. It's 2 to the power of something. That's because it's binary to the power of,
32.
forget that for a second. The question was, if you remember, because I see you're panicking, you're not thinking about the real problem, you're thinking, oh, what number can I throw at him?
Only
The question was, how many different combinations can you store in a byte? So what you need to think of is, how big is a byte, right?
2 to the power of 7.
Kind of. It's 8 bits, right, we said?
Was 2 to the power of 0 not the first one? Oh no, it's 2 to 2, yeah.
It's 2 to the power of 8. So, if I have for myself 8 boxes, yeah, 8 clearly distinguished spaces, when I can put a hole, a wave, or anything like that, if I have a space of 8 bits, I can interpret that as 256 alternative values. I can write a 0, a 1, a 2, a 3, a 255. I cannot write 256 because I had the 0. Or if I don't need the 0, I can write 1, 2, 256. If I don't need 1, if I can start from 1,000,000, I can store a number. So I put it differently. If I know that I will never have a number that is less than 1,000,000, I have 256 combinations from 1,000,000 on. So it's 1,000,001, 1,000,002, 1,256. It's arbitrary. It's whatever we agree that we translate our idea into. We can say that we have a map of 256 combinations. 1, 2, 3, 4, 5, 256. And we can say, I don't know, arbitrarily here, 4 equals A, 5 equals B. Completely arbitrary. The only important thing is that when I read that information back, I use the same table to decipher it. Okay? Am I making sense? So we have some physical space in which we are storing information. These informations are physical, really. We can attribute a numeric value to that, 0 or 1, or we can attribute any other value to that, true or false, or we can attribute a literal value if it's a sequence of true, 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 false, 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 then I will consider it to be an A. If it's false, 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 true, 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 it's a C. Whatever. Whatever physical value I read, I must be able to interpret. Okay? The number of boxes are finite. There is no such thing as an infinite computer. You know how many boxes you have available. They can be expandable. You can slot in another USB stick and write more onto that. You can take it out and you lose that capability. You can be on the network and distribute that information on several other computers and store a bit here, a bit there. You can have 23 Dropbox accounts and use them all together, but they will always be on some sort of physical layer. The line drops, your network is unplugged, whatever, that information is gone. It needs to be physical. Okay? Now, the reason I wanted to come to that is because we now understand that we have standards. This is one of them. This is the ASCII standard. Have you ever heard of ASCII? Spelled A-N-S-C-I. That controls your life. It's ASCII all the time. Except when it's not. I wanted to make a clear difference here because I want to understand the problems associated with this. Now, we said an A is character 81. No, sorry, I think it goes 65. Yes, so it's number and symbol, right?
Why 60? Why did it start there?
And the only possible answer is, why not? You have a better option?
Fair enough.
It's completely arbitrary. It's a round number in a sense. I know it doesn't look like one, but it is a right number because you have 1, 2, 4, 8, 16, 32, 64, 128. These are the values of all the bits on a decimal byte. Yes. And ASCII is actually a 7-bit standard. So you can fit the ASCII table, you know, the largest number is 127. You can fit it in 7 bits. It doesn't need the 8-bit. So 65 is actually 1000001. Nice and round. Completely arbitrary, but if this answers your questions. The next thing I wanted you to understand is that, what is that?
Lowercase.
So, if we want to distinguish a lowercase a from an uppercase a, we have to find space in that combination set. Yeah? So, actually they attributed two different numbers to a. The lowercase a is 97, the uppercase a is 65. That works, that's nice. Now, we have ways of talking to each other just by exchanging numbers. I can tell you hello, or I can tell you 72, 69, 76, 76, 79. You read those numbers, go to your ASCII table and say, oh, he said hello. Okay? We are now using a standard to communicate. This is very important. This might seem trivial, but it ain't. The A380 Airbus, yeah? Problems in coding numbers, conversion from imperial to metric, due to misunderstanding the way in which information was stored in bytes, millions of dollars of costs and delays. Big problems. What's the limit of that?
It's the English alphabet.
It's the English alphabet. There is no Chinese symbol in there, no Indian symbol, no Thai symbol. So if you want to use those, you have to have a different convention, right? Can you fit that into a byte? Answer is no, because if you consider, for each byte that you read, you transform that into a letter, you only have 256 possible alternative symbols. That's it. There is no way around that. There is no way to put even a tiny, tiny fraction of information more in there. No way. Physical limit. If you have a byte, the richest set of alternative combinations that you can put into that is 256. So if you want to store more than 256 different symbols, you must use more than one byte. That's very simple. You had a question, sorry.
No, I thought we were talking about this itself. I didn't think you meant the other conventions on top of it. This can be stored in a byte, can it?
So,
This ASCII English alphabet one can be stored in a byte. Because it's 128.
yeah, this can. Yeah,
if you
this
want
can.
more than that, more
If you
alphabets
wanted
or-
to have, actually you have space for 128 more.
Yeah,
Yeah, because you can store up to 256.
yeah,
But if you want to store 129 more, no way.
yeah. No, that's fine. Yeah, I was just confused.
Everybody happy? We now know that these physical characteristics of the way in which computers work give us limits and give us power in the definition of arbitrary conventions to transform something in something else. We now have ways to store letters. How do I store a whole sentence? That's what we just said. I can make a decision that we store a character for each byte, and that is not enough, because if I do that, I will have to give up all Indian symbols. There is no space. So, if I store, but let's suppose that we use that convention and we use a byte for each character. How big is a file for any of our sentences? So you know how big a file is, right? You can go right click on it and tell you, it's going to tell you this is 3 megabytes, 2 Ks, 3 bytes, whatever. So a file for a sentence, if we use that convention, is going to be 1 byte for each of the characters in it. You want to try? Open Notepad. Do you have Notepad on this computer?
Yeah.
So write whatever character you want in it, one single character, save as on desktop or wherever you want, right click properties, and it's going to tell you how big that is.
It's only one character.
Yeah, one single character.
This 1 byte.
1 byte.
Is that what it's telling you?
Size on this is 4 kilo.
4 kilo. Yeah. So it's telling you that the size on disk,
And the size is 1 byte.
so the size is 1 byte, and the size on disk is 4K.
512 bytes.
In your case, it's 512 bytes. So we are seeing some discrepancies here. You have, the file size is always the same. It's 1 byte. If you type another, try and say now, go back to that file and write A or whatever character, go to the next line with the return, and then write another character in. So we now have 4.
4 bytes.
4.
Bytes.
How annoying is that? Why does it make sense for it to be 4?
It's doubled.
Because it's
6
the
characters.
second line. Okay.
So we have 1 byte that gives the first character. We must have somewhere another byte for the second character, and we have 2 bytes unaccounted for. Correct? Those 2 bytes must be the idea of going to the new line. Yes? Is the return. But so we pressed 1 button, A, and it was 1 byte. We pressed 1 button, return, it was 2 bytes. Correct? Why?
You have to move right across and down.
That's exactly what it is. Because if you are talking about, if traditionally you had a different command to tell the printers to go back to the initial line and to feed, you know, are you familiar with old typewriters, right? There were 2 different commands to go back to the first line and to a new line, and to make the paper advance. These are 2 commands. So one is coded 10 and one is coded 13. So ASCII does not only code letters that we see, but also commands that can be interpreted as meta characters. This idea of going forward, rolling up the paper and going back to the initial column of your paper. These are 2 individual commands, and they are stored individually in 2 different bytes. So, how big a file for a sentence? It's 1 byte for each characters plus 1 byte for each of the commands that are adorning our documents. Return being a special case, tab being another special case, and so on. Yes?
Alright, is that when you were saying there's 256 alternatives?
To under 56 possible combinations, yes.
For a byte.
For a byte.
So one character, every character is made up of 256 like 0 and 1.
No, it's made up of 8 of them. 1 byte, 8 numbers, 8 binary numbers,
Yeah.
8 bits,
Yeah.
okay, that I can read together, forming 256 possible combinations. So, just as if I had a space in decimal, okay, I can write down a decimal in decimal convention, okay, I have 2 spaces. I can write a number here that is either, I don't know, 35 or whatever, goes from 0 to 99, yeah? That's the range of variability of having 2 spaces. It's 100 combinations, right? Similarly, for binary numbers, I have 8 bits. They can all be either 0 or 1, 0 or 1, whatever. And the range, the possible combination size is 0 to 256. Oh, sorry. 5, if I include the 0.
With 2 spaces, you only have 100 combinations.
In decimal. In decimal. So if I have the ability to write any number from 0 to 9 in there.
Yeah.
If I reduce that ability, and I can only write 0 or 1s, of course the richness of my vocabulary is decreased, therefore the amount of possible combination is reduced. I'll give you an example that is easy to understand. If I only have 1 slot of binary, I can only write a 0 or a 1. So you have 2 combinations, 2 alternative values, right? If I have 2, I have 0, 0, 0, 1, 1, 0, 1, 1. So if you give me 2 spaces where I can write something, I only have 4 combinations, having 2 spaces. For each space that I add more, I double that. Because I can have all of these plus a 0 in front, and all of that, all of these plus a 1 in front. So that's why I'm doubling them, right? It's now becoming real for you, I suppose. You're now understanding that if you want more possibility to write more different values, you need to have more space. It's very simple. Same applies to decimal numbers, same applies to any notation.
Can it become very confusing when you have a lot of space that can more problems?
To the human, yes. To the computer, no. Having a lot of space to a computer is just a matter of time to go through that and reading it, and then splurting out a name or a B or whatever it takes. Never confusing. Can be buggy, but that's a different thing. Right, so we now have understood another idea. This idea of how big a file is intriguing because we have a file size and then we have a size on disk. Well, I thought it was on a disk anyway. So what does that mean?
Needs to have an identity on the disk so recognise what it is.
Very good. So, if I have I don't have a thing today. I'm getting a tune for this. Anyway, I'll survive. The idea is, is that our computer is not born with Windows or anything like that. Windows is installed on our computer. So, as it is, my computer is just a bare prairie of boxes where I can write all those sorts of numbers. This is my memory, this is my disk. It's just a big array of zeros and ones. Alright? Huge array of zeros and ones. This is my disk. This is my memory. And the CPU goes through the memory and does things according to what it finds there. We'll look into that later. But I need to have some space where I actually write, look, that file there is not just the idea of A, return B, whatever you typed. It has a name. You gave that file a name, right? Whatever it was Pluto.txt. It has an extension. It has somewhere an idea that was created on the 14th of January 2014. All of this information, you know you can read, right? When was the date it was created, last modified, all of these things are stored on your disk. So if this is your disk, there is a portion of that that is actually retained for storing all of that information. Pluto.txt. And the data is actually somewhere else. So here I have 65 for my A, 10 and 13 for my return, and whatever, you type the B, 66. This is the file. So this is the content of the file. This is, again, it's never going to be text, but it's going to, it's the equivalent of those letters into binary. And also you need to know that that file starts 1, 2, 3 on the 4th row. Because when the computer needs to go and read it, it needs to know that it starts from here and not from here. Okay? And then it is 4 bytes long. If I don't know that, I can start reading a 65, a 10, and 13, a 64, and then I can go on reading the next things, right? Tell me that it's finished. No, it seems trivial now. If nothing tells the computer that's where the file ends, the disk goes on. The disk does. Goes on for a long stream of bytes. So somewhere you have to tell the system, well, yeah, that's where it ends. It's only 5 bytes long. So what it was telling you actually in different situations is that the size on disk is somehow, somewhere 4K and somewhere 1512, right? Now, of course, these are all multiples of binaries, 4028 and 512, which is going to be, it's 256, 512 is the next multiple of 2. Right? So these are all multiples of 2 because all of this space has been arranged and say, well, depending on the disk, we have clusters of, blocks of 512 bytes, and we give each of them a number. So this is number 1, this is number 2, this is number 3. So actually I'm coming here, I'm not saying it's on the 4th line, I'm saying it's on cluster 2. But if it starts on cluster 2, then it's using all of cluster 2, because for the next file, I cannot go and tell the system it's starting on cluster 2.5. I don't have space to write that. So by putting 4 bytes here, I'm actually using up all of the space of that cluster. It's just because I don't have ways to tell the system, yeah, there is some spare space there, we'll use that for another file, writing it from from the end backwards. It's possible to do that. It's possible to conceive a computer that works like that. It's just that these systems don't work like that. And yours has probably a larger disk and has allocated larger clusters. So each file that you store on that file, on the disk, wastes at least 5Ks. And yours, probably a smaller disk, wastes, doesn't waste, allocates blocks of 512 bytes at a time.
Is that like that, that defrag? Is that when it starts moving all around?
Yeah, I didn't go into those details, but this idea is that actually you can have certainly have files that span across multiple blocks that are larger than 512 bytes. So, if you have a situation where, let's say that you have blocks that are just these lines, you can have a file that starts here and says blah blah blah, whatever it is. Unfortunately, it cannot continue here because this is already occupied by another file. So, it can use the last few things to say, it continues at number 32, down here, right? So the computer goes in and reads the first part and says, oh, no, wait, I have to skip and jump to this point to continue reading it. The defragmentation of a disk is the process of bringing together all those bits. How do I do that? Well, I must, if I want to write it contiguously, I will have to put this information somewhere else and then move that information up there, right? So what the computer actually does is to come here, read all of that and copy it somewhere else, and then go back to the index and say, you know that file that I told you started there? It actually now starts somewhere else. And the order in which these things are done is important, because if you first change the information in the index, and then you make the copy, and something goes wrong, you have lost your file. Make sense? So, clever computer scientists will make this thing go, first I move it to the new location, and then I go and update the index of where to find it. Then I go and move all the second block up here, and then I go and can remove this idea that tells the system, now skip this much bytes. Yeah? Is it working for you? To some extent.
It's like an automated stock check.
Say again?
Like an automated stock check.
Yes,
where
yes.
It should be, make sure it's in the right place and move if it's not.
Actually, there are applications that do that for you, that go and check that the information is where it's supposed to be. It's much more. It's much more complicated than that. Actually, a file system. It can have numbers every now and there that give you error control, so that you maybe have a sum of all the 4 bytes down there, so that you say, well, it's 1, 1, 1, 1. Is the sum 4? Yes. It means that my data is correct. You go and read 5, you say, what? Wait a second. Some of these must be wrong. There are ways to store this information though, so that even if a limited amount of those individual numbers are lost, its redundancy allows you to reconstruct the original data. So basically you save the information multiple times, so that when something gets lost you can always go back and reuse the right bit of information. Alright? All of these things come with the fact that unfortunately all of this needs to be physical at some point. I think we'll be dealing with colors in your profession. Do you think we'll be dealing with the fact that people need to exchange information about the color of something? How does it happen? And the traditional response is by magic. And it's not by magic. It's by setting up a convention that we agree upon.
Each, yeah,
Is it the same way?
each combination of colours has a unique series of digits.
Exactly. That could be very expensive though. Yes.
But like, when I look at that, you've got like the different colours overlapping each other. How does, there's obviously lots of gradients of a
Exactly,
colour.
yes.
Or there's going to be thousands of alternative series of digits. When is this going to end?
We have to decide that. And we have decided that indeed. First of all, a question. RGB, are they arbitrary things?
Perfect colours.
Yeah, but is that, why RGB and not pink, yellow?
They're the three main primary colours that make up the other colours in the spectrum.
In the spectrum?
In the visible spectrum.
In the visible, you're getting closer, in the visible spectrum. What is the visible spectrum?
What the human eye can see.
Exactly. So we have three types of receptors in our retina. The one that pick up the red, the one that pick up the green, and the one that pick up the blue. This is physics, but it's also deeply, deeply connected with our vision. Our eyes have three physical different receptors: red, green, blue. So without that, we wouldn't see color. Dogs have four types, I understand. That might be wrong, but you know, we see RGB because our eye sees RGB. We are kind of clever computers. We have sensors that pick up wavelength and transform that into our mind, into the idea of a color. But hey, that's complicated. Computers can easily emulate that through screens like this. If you look close enough, you will see the red, the green, and the blue pixels. You don't?
How it works.
On
Very
TV, on a really, really old, like 1990s television set, if you look real close, you really can't remember seeing.
I'm not sure whether these are high definition computers. They might be, but you can tell them. If you this is an RGB color. This is a Trinitron, old model, Sony. Those are lights that switch on and off because the computer process tells them you should be 20% on green, 50% on the red, and completely off on the blue.
So it's,
Yeah.
I was just going to say, is that why photo software, sometimes on screens, they give you the contrast settings and it's normally not red, green, or blue, but you can move the colour like more blue or more green.
So RGB is not the unique way to obtain color, but yes, it is. You can easily control how much you're going to stimulate the visual perception of our retina through the different channels. So it's all hardware. It's all hardware. All these things that we give for granted. Oh, it's RGB. Of course, it's RGB. We don't even realize that it's hardware in our eyes and it's hardware on our machines that is doing that. But anyway, how do we store such a thing then? So we know that we can make up a color by defining the proportional intensity of the red, the green, and the blue. Now that you know everything there is to know about binary codes, how do you do that?
Value for varying degree of intensity of each colour.
Exactly. you give a value to the intensity of red, you give a value to the intensity of green, and a value to the intensity of blue. So, in the past, there were situations where you had a graphic card that would display 16,000 colors. Have you ever 64,000 colors? I think 64,000 colors. Have you ever come across anything like that? Is this something that you are familiar with? It?
I think so, yeah.
But now they are obsolete, of course. Everything is 32 bits or more. When I say 32 bits, does it sound familiar? What does it mean?
This is like just processing power, isn't it?
No, we're talking about colors.
What's the potential combinations?
Exactly. 32 bits meaning how many bytes?
256. 32, what else?
32 times 8 to the power of...
No, power is not involved in this. So if I have 32 bits, it means that I have a string of 32 bits, right? How many bytes? Each byte is
Oh, 4.
4, exactly. So it's 4 bytes. So see, these are simple questions. I know. After some time, you just go, oh, it must be something with a power of 22, right? But no, some questions are still simple. So a stream of 32 bits is actually a stream of 4 bytes. It's the same thing, because each of them is 8 bits. Now, that's an interesting number, 32 bits. What does it mean? Well, it means that there is a component for red, a component for green, a component for blue. It kind of goes, you can probably infer that there's going to be 1 byte for the red and 1 byte for the green and 1 byte for the blue, which means that you can discriminate 256 intensity levels for the red. And same for the green and same for the blue. If they are all full on, you'll see a white color. But that's your mind. You're actually receiving a lot of green, a lot of red, and a lot of blue. And your mind receives that. Exactly. It doesn't receive white. It receives a lot of red, a lot of red, and it interprets that as a white. If it doesn't receive anything, 0, 0, 0, it's a black, no color, darkness, black. There is 1 byte missing. So we have 1 for the red, 1 for the green, 1 for the blue. The last one.
Is that where K comes into? Is that the K? I can see MYK.
No, that's another way of encoding color.
So
I won't go there today because you will kill me out. But there is one thing that is actually transparency. Huh? Yeah, because I can have images overlapping, and around the edges, it's nice to say, well, this color would be that color, but it's actually faint. It's like transparent, so everything is fainted down. So one is this so-called alpha channel, which means, yeah, I can actually have an image that stores a piece of the image which you can see through. It doesn't need to be a square image, right? So that brings us to the next question. How do you store an image? I'm asking these things because you are going to have to move images around. And with some images you can do stuff, and with some other images you cannot do stuff because of the way in which they are encoded, because of their file format. We're almost there, right? I promise you I'm letting you go in a couple of minutes. But come on, we have an image, right? And you know that. You have all played with Photoshop and stuff. So you know that you can actually explode that image in fractions, not pixels, right? And you can say, well, that pixel has that color, that other pixel has that other color, and so on. So, how big is a file that stores such an image? First of all, you have to decide how do you store each of the colors, but we said that. We said that you can store actually, let's say you're storing 3 bytes for each pixel. Intensity of red, intensity of green, intensity of blue for each of them, because they are different, right? Or they can be different. That goes into compression. We'll look into that. So this one here is actually, if I want to save that image there on my disk, lot of space, I can actually go and say blue, which means if I'm storing things as in red, green, blue, I'm storing 0, 0, 255, means full blue, right? And then the next bit comes and it's another blue, so I can store 0, 0, 255. And another one, 0, 0, 255. And then a green. What do I say?
2550.
0, 255, 0. Each of them is a byte really, and it's written in binary, of course, but you know, just for simplicity. Are you following? So, how many bytes do I need to store the whole image? So it's 16 pixels times 3 bytes each, correct? Yeah? Is that enough?
Is there the thing for line as well?
Exactly. If we have a stream of 16 pixels, we should somehow know when the new line starts, right? Because it could be a single stream of 16 pixels long, it could be a single stream of 16 pixels tall, or it could be 8 and 8 or 4, 4, 4, 4, correct? So if I don't know that, how can I reinterpret that image? So actually I need to start saving some information such as I don't know, a couple of bytes to store the width. Why do I say a couple of bytes and not 1 byte? Because in this case it's 4, so I can save 4 in a single byte. Because I can save up to 255. But I want to save 2 bytes because I want to have images that can be as large as 64,000 bits. Or probably more. Sorry, pixels. Are you following? So the way in which I define the standard of writing information determines the type of information I can write. If I only store 1 byte for my width, the time as soon as I encounter an image that is larger than 255 pixels, I cannot save that number. There is no space to save that number. Because the second byte that I have available, it's already the color of the first blue or red, whatever. So it's important that we have standards that allow us to save the information that is flexible enough to enclose all we need. So I'm talking too much today, but you seem to be doing well. Can you make it for 15 more minutes? Are you all positive? Yeah? Okay. Is that the only way to store a picture? if I'm wanting to convey the idea of an A-shaped object, I can actually store it as a sequence of pixels that are or given color, or I can actually store it as an idea of 3 lines that intersect at given coordinates. Makes sense? You see how I can transform those lines into the bitmap? Kind of, because there is a bug here. Clearly, this pixel here should be red because it's crossed by the line. And similarly, this one here probably should be red as well because again it's crossed by the line. But you see, you know, you get the idea. I have the idea of these 3 lines, and then I can switch on all the pixels that these lines intersect. The advantage of that is that if I see this A very small, it's nice, it's neat, it's very clearly visible, but as soon as I scale it up, it gets distorted. So I see the boxes rather than seeing the A. Okay. However, if I have this idea, the idea of the 3 lines, and I scale it up, I still have the idea, the full idea of the 3 lines. So it's going to be neater, the graph that I obtain if I want to scale the vector representation of that symbol. Yeah? This is the big difference between vector graphics and bitmap graphics. Okay? Have you ever heard of that? This idea of vector versus bitmap? You have? You all have?
I've heard of vector and of bitmap, but I've not heard the idea of versus each other.
Oh, okay. No.
To me, that just it looks like vector is more accurate than bitmap. That's all I'm saying.
Vector is generally, well, accurate.
It looks a bit smoother because you've got.
Yeah, but that's because I actually decided to show an unsmooth image. I could actually have a beautiful A here with all the serif, Is it working? So this here is actually an image. It's a bitmap image. This one. You don't see it rough around the edges because it's at the correct resolution for the screen. All right, but it's a bitmap. If I scale it up more than that, then I can start see the pixelation. Right.
The vector is plotted on pixels on a linear basis, so that no matter if you scale it up or pixels themselves get pixelated, the lines stay the same.
Yeah.
Between
Yeah, that's the idea. So the way in which we store this information makes a difference to what we can do with that information afterwards. So, but clearly, and potentially actually I get some benefits in storing it as a vector. Can I ask you how many bytes or bits do you think you would need to store these and these? So the same is the A as a bitmap and the A as a vector?
Same.
Hmm?
Same.
Why is that?
Same squares.
No, as a vector is not the same squares. I can represent it as the same. You look at the three black lines, not at the red dots. Eh?
Okay.
So
Is there more information in the vector image?
I think there is a different purpose of the information in
It's
the
more like coordinates, isn't it?
There are smaller coordinates, I don't know. Are they?
No, like the positions are marked rather than the shape.
It is the position, so it's coordinates. How do I store a coordinate like that?
X and Y.
X and Y coordinates, of course. But in binary, I can, I'll give up soon, but I think these are actually very, very important because we are actually coming to the point of understanding the difference between drawings and building information models here, all right? We're now really there. So it's probably worth moving on to something that is more realistic for you. An architectural drawing. How do I store it? A drawing like that. I can store that as an image. So I can say, well, there is a pixel there that is of that color, and then another pixel of that other color. And that, if I scale up, I see big pixels and no detail, right? Or I can go and look at the vectors. Ah, that's very interesting. The vectors. So I'll try and draw something for you here. I have something like this. Whatever. This is the Italian convention of drawing. This is the door. Right? How do you store this information?
Coordinates.
So you place a coordinate system around it. Yeah? And then you tell, okay, what?
The line starts at whatever point from 0, 0.
So this is whatever, x1, comma, to separate the x from the y, whatever, 4, this is 1, 3. Yeah? So I have a line that goes from 1, 4 to whatever, 6, 4. Yeah? This point here. So somewhere I have this concept of a line. A line? How do I say the idea of a line? I can write line, or I can write 0. 0 means line to me. I'm happy. 0, and then 1, 4. Okay, how do I write that 1? Let's, just for simplicity, 1, let's say we write it as a 32-bit floating point integer. Don't worry, floating point number. Don't worry about that. It's just to say that you can, we haven't seen that yet, but we've only seen the ability to write integer numbers, 0, 1, 2, 3. It's also possible to write something that has a comma somewhere along. Okay? So, and we say that to have a good precision, we have 32 bits for that. So, 4 bytes for the x, 4 bytes for the y. Okay? And then what?
Well,
I need to know where I finish my line, right? So I probably need to know that there is another line, that the end of that is another 4 bytes for the x, another 4 bytes for the y. And so this initial idea of a line is taking me 4 by 4, 16, and 1, 17 bytes. These 17 bytes tell me that there is a line somewhere on my drawing. I can zoom in and that's going to be still neat, right? I know exactly where it starts, exactly where it finishes. Then there's going to be another line that goes down here, correct? So this is one, this is second, this is third. So I need 17 bytes for the second line and so on. What about this thing here?
Is it a series of points?
Possibly. I can write it as a series of points, or I can write it as I start my sequence with 1, which means arc. Oh, good, arc. So an arc has the center in this coordinate here, so 4 bytes for the x, 4 bytes for the y, and then what I need is the angle that I start with and the aperture of the arc. If I have all that information, I can rebuild that, right? If I have these 3 information, I can, this coordinate center, angle, another 4 bytes for the angle of start, and another 4 bytes for the angle of finish. Yeah, I have the whole thing. I know where to draw my arc. However, you probably have noticed that this was actually dotted line, like a dashed line.
That belongs to whatever layer has whatever line type assigned.
Ah,
to it.
okay, we didn't discuss layers here. There is no layer. You see my point? If it's not in the file, it doesn't exist. If I haven't written somewhere that there is an idea of 255, which is a code, I arbitrarily decide whenever a new layer starts, and it's followed by a text of 24 characters where I write the layer name, plus whatever bytes I need to store the type of line, whether it's dashed, whether it's continuous, whether it's double, whatever. I need ways to agree. How do I save that information? So at some point I will have, this is the layer of all the lines, and then I have another layer, 255, that is called arcs, and then I have 1, which is my arc, sorry, this is another line, that's what we propose. 1, which is one of my arcs with all the 4 coordinates and so on. I have now written down all the information that I need to reconstruct my drawing. That's beautiful. That's exactly what I needed. Is that BIM? No. Damn it.
Is that the programmer writes the convention for the different elements?
Yes, the programmer must have some level of understanding of what are the information types that he's dealing with and ways to store them on the disk for you to be able to open and stand back. Yeah? So, my big question is that BIM? And the real answer is no. What is that?
Drawing.
Data.
Say again?
Data.
It's a drawing, it's data, but it's not the answer that I'm not looking for. They're both true, but not.
Basic.
It's CAD. Yeah? That is CAD. So that is a way for you to store a drawing. Not anything about a building. Those are lines. What does the computer know about that?
They start at one point to end up another and whatever coming
And
back.
nothing else. It only knows that there are some lines, some of them are close, some of them are far. No idea of a door. None whatsoever. You know, another way I could write a file, that file down there, like this. Same coordinate system, wall, starting from I can write, there is a wall, starting at 1.3.5. Wall starts at 1, 3.5, and at whatever this number is, this was 6 we said, so that is 10, 3.5. So the wall actually goes all along, it's the same wall. Ah, interesting. It's the same wall, it's not four lines here and 4 lines there. The same idea of the wall. And then there is another, and then what also we need is thickness equal whatever, this is 1. And then there is a door that has a center at